In this video, we'll demonstrate how to solve compound interest problems using Excel. Let's consider several problems. The first problem is this. Aniko invested $5,600 at 6% compounded quarterly for 4 years. What will be the interest earned? In this table, here we already inputted the necessary values for our solution. The present value is 5,600. The rate is 6%. Stated as rate per 1, it is 0.06. Compounding frequency is 4 because there are 4 quarters in a year. Term is 4 years. So we'll start by finding the future value. Future value is found by function fv. Excel's function fv is designed to find future value of annuities, but also of investments under compound interest. First comes the rate. This rate in Excel is periodic rate. You need to find periodic rate in order for this function fv to give you the correct results later on. So the periodic rate is the nominal rate, which is in cell B5, divided by the number of periods per year, which is in cell B6. So B5 divided by B6 is the periodic rate. Next comes the number of periods. The number of periods is the number of compounding periods in a year times the number of years. So B6 times B7 will give us the total number of periods. Next comes payment. Because this is not an annuity, the payment is 0. There is no periodic payment in this problem. Next comes present value. So the present value is 5,600. And then we need to specify the type of annuity. Because that's not an annuity, we don't care about the type here, and we can use any type of annuity. So we'll use 0 here for end of period annuity. Because that's not an annuity, that will not make any difference. If I press enter, the answer will be $7,106.32. The thing is that Excel gave us the answer as the negative number. That's because we made our present value positive. So present value was treated by Excel as amount incoming, and the answer, therefore, the future value would be amount outgoing. So if you put the money into the bank from the position of the bank, that money is incoming. But then the future value will be picked up by the customer from the bank. That's why from the position of the bank, future value is the amount outgoing. In order to display future value as a positive value, either we should put negative sign in front of future value, or we should make the present value negative, like so. So let's choose this option. We'll make that present value negative, meaning that the present value is the amount outgoing. So the future value will be the amount incoming and will be displayed as a positive number. Interest is the difference between future value and present value. So future value minus present value. The answer is therefore $1,506.32. For demonstration purpose, we can solve the same problem with algebra. So we can find future value using the formula. Present value 1 plus I exponent n. Future value, therefore, is going to be 5,600, 1 plus 0.06 divided by 4 times 4. So we have 4 compounding periods per year and 4 years. If we now compute it with a calculator, we'll find 7,106.32. Interest is found as future value minus present value, which will give us $1,506.32. Of course, we received the same result as with Excel. Let's proceed to the next problem. How much money was invested on October 12, 2017 at 5% compounded daily if the investment matured to $6,700 on August 5, 2018? Again, this table here contains already data that we need to use to solve this problem. Future value is 6,700. The first date is 12th of October 2017. The second date is 5th of August 2018. The rate is 5% compounded daily. We'll start solving this problem by finding the number of days between those two dates, D1 and D2. The number of days, of course, is found very easily. Once you enter those dates correctly into Excel, the number of days in B11 can be computed as B7 minus B6. We have 297 days between October 12, 2017 and August 5, 2018. The present value is found in the following way now. We'll use present value formula, and the present value formula in Excel again calls for the rate. The rate is periodic rate, so we'll need to find periodic rate, which is B8 divided by number of periods, which is B9. Then comes number of periods. Because this rate is compounded daily, so the period is a day, therefore we already have the number of periods in B11. We have 297 days, and that's the number of periods. So we'll put B11 here for number of periods. Next comes payment. Again, that's not annuity, that's why the payment is 0. Future value. Future value is given here, which is 6,700. Then comes type. Again, because that's not annuity, it doesn't really matter, but we'll select 0 here for type. If we press enter, again, the present value will be given here as a negative number. The way to fix that negative number is either to put negative sign in front of PV or negative sign in front of the future value. The reason for this was already explained. That's the difference between amount incoming and amount outgoing. If we press enter, we have the present value computed here. That's the amount of money which was invested on October 12, 2017. Now let's see how this problem should be solved with algebra. We will be using present value formula, which is future value 1 plus I minus n would be the exponent. Present value is the future value, which is 6,700, 1 plus the rate, which is periodic rate, which is 0.05 divided by 365, and the exponent will be minus 297. If we compute this present value, we'll obtain 6,432.90, which is exactly the same answer as we obtained with Excel. Let's proceed to the next problem. The investment of 6,700 has provided the interest amount of $300 in 1 year and 2 months. What was the effective rate of interest? To solve this problem, let's remind ourselves what effective rate is. Effective rate in our course is rate, nominal rate, compounded annually. Basically, we need to find the rate compounded annually, which has provided the interest amount of $300 in 1 year and 2 months. In this table here, we already have information entered. 6,700 is our present value. Interest is $300. The term in years already has been calculated. You can see it is 1 year plus 2 over 12. 2 months over 12 months in a year. So this annualizes month. And the total will be 1.167 years. Well, let's start by finding the future value. Future value is the present value, of course, plus interest amount earned. So the future value is $7,000. Now we'll be looking for the effective rate. Effective rate is the rate compounded annually. In Excel, that's the function for rate. Again, this function for rate is for annuities, but we can use this function for such problems as well. First is the number of periods, the number of years. So the number of periods in this case will be in cell B7, 1.16 in period years. Then the payment, which is 0 in this case, present value is going to be in B5. We'll put negative sign in front of the present value, meaning that that will be the amount outgoing. The future value is going to be in cell B9, but you should pay attention. If we make present value amount outgoing, so the future value is going to be positive amount incoming. That's very important for this formula. Next is 0, so end of period for this, because it's not an annuity, it doesn't really matter, so we'll enter 0 here. Next parameter is optional, and in this problem we don't need it, so we'll enter nothing there. Close the bracket and press enter. Excel gives the answer in B11. However, please note that the answer has been rounded right now, so we need to select cell B11 and make sure that we select the necessary number of decimals. Here I selected 2 decimals, and the answer appears to be 3.83%. Let's compute the same thing using algebra. The formula for I is future value divided by present value, 1 over n minus 1. I is future value, which is 7,000, divided by present value, which is 6,700, 1 over the number of periods. In this case, we'll just write here completely 1 plus 2 over 12. That's the number of years. And the period is 1 year, I remind here, because the rate is effective and is defined as the rate compounded annually. So the period is 1 year. And therefore here is given as the number of years. 3.83% rounded to 2 decimals. I remind that we found I, which is the periodic rate, but because this rate is compounded annually, period is 1 year. And in this case, I, periodic rate, is the same as J, which is nominal rate, and we use sometimes letter F to speak about the effective rate. So for effective rate, because it's compounded annually, the periodic rate and nominal rate coincide. We can use this special letter F. This answer we obtained, 3.83%, is the same as what we got with Excel. Now let's consider another problem. 2 banks, A and B, offer the same amount of interest rate for loans. If Bank A offers 3% compounded daily, what nominal rate compounded semi-annually does Bank B offer? Here we need to find equivalent rate. So we need to find the rate compounded semi-annually, which is equivalent to 3% compounded daily. Excel does this calculation in 2 steps. First, we need to find effective rate using Excel, and then we'll be using effective rate to find that new nominal rate. So in Excel, we have to find effective rate first. To do so, let's do it in cell D6. We will use the function effect. This function effect first asks for the nominal rate, which is known. In this case, it's going to be 3%, which is in cell B6. And then we need to specify number of periods that nominal rate is compounded, and that is in cell B7. That's because 3% is compounded daily. If we let Excel now compute this, we find that the effective rate, which is equivalent to 3% compounded daily, is in cell D6. Now we are ready to find the nominal rate compounded semi-annually in cell B9. To do so, we'll use the function nominal. That function nominal will require effective rate to be inputted, so it's going to be in cell D6, and then number of periods that we are looking for. So in this case, 2, because we are looking for semi-annually compounded rate. If I press enter right now, I find that Bank B should offer 3.02% compounded semi-annually. That's rounded to 2 decimals, and that will be equivalent to 3% compounded daily. I can actually state this answer as percent and increase decimals to 2 decimals, and that will be the answer in cell B9. Of course, we used cell D6 in order to find effective rate that we used later in cell B9. What we can do, we can make all computation in cell B9. So instead of D6 in this computation, I can insert another function which will make that computation for me without the necessity of utilizing auxiliary cell. So that's basically calculation that we made in cell D6, but now that calculation is inside our nominal function. The answer, of course, will be the same. With this, I can simply erase cell D6, and we have a cleaner solution. Now let's use algebra to solve the same problem. The formula in this case is formula for I2, which is 1 plus I1. That's the formula to find equivalent nominal interest rate. M1 divided by M2 minus 1. M1 is the number of times that known periodic rate I1 is compounded, and M2 is the number of times rate I2 should be compounded. So I2 is 1 plus I1, which is in this case 0.03 divided by 365. 365 is the number of times that known rate is compounded, divided by the number of times we are looking to compound the rate I2, minus 1, 0.0151124339. Of course, what we found right now is periodic rate. If we now try to find J2, which is the nominal rate, that's going to be I2 times 2, because I2 is compounded semi-annually, so there are 2 compounding periods. The answer will be 3.02% if rounded to 2 decimals, which is exactly the same answer as we received with Excel. Our next problem reads, an investment of $56,000 accumulated interest of $2,000 growing at 4% compounded semi-annually. If it continues to grow for the same amount of time at the same interest rate, how much more interest amount will it earn? To solve this problem, we need to find the time necessary for that amount to continue to grow. And the problem is stating here that it's for the same amount of time the investment will continue to grow. We'll use the first part of the problem to give us the information to find the amount of time. The information already has been pre-entered here. So in cell B6, we have present value $56,000, then we have interest $2,000. In cell B7, the rate is 4% compounded semi-annually. We'll be looking for term in cell B12. The function to find term is NPER. NPER stands for number of periods. First, we'll be looking for rate. Again, this is a periodic rate. So we'll take that nominal rate in B8 and divide by the number of periods, which is in B9. That will give us periodic rate. Then payment. Again, because that's not an annuity, payment is 0. Present value. Present value is 56,000 in this case. Let's put negative sign in front of B6 to designate this as an amount outgoing. Next is the future value. The future value in this problem will be our present value plus interest earned, because future value is present value plus interest. Then for end or beginning of period, it doesn't make any difference because it's not an annuity, so we'll select 0 here. Press enter, and we find the term, which is 1.77205. But what does that term mean? That's the number of semi-annual periods. Let's type here, number of semi-annual periods. Now let's proceed to finding the future value. Future value is the function fv. First comes the rate, which is the periodic rate, which is B8 divided by B9. Then the total number of periods. This total number of periods has already been found in cell B12. Payment is 0 because that's not an annuity, and the payment is 0. Present value has been updated this time. We started with present value 56,000, but that present value has accumulated interest already of $2,000. Now we continue with our investment. So the new present value is going to be found as 56,000 in cell B6 plus $2,000 in cell B7. So then we'll select either 0 or 1, which will not make any difference in this case because that's not an annuity. So we'll select 0. If I press enter right now, I'll find my future value. Now this future value is given, of course, as a negative number. That's because our present value has been given as a positive number, as amount incoming. To fix this, I can simply put negative sign in front of my present value here. The final thing is to find the interest. The interest is our future value minus that new updated present value, which is in cell B6 plus interest, which is in cell B7. So from our future value, which is 60,071.43, I subtract that updated present value, which is in this case is going to be 58,000. The interest amount thus is found as $2,071.43. Let's see how the same problem is solved by using formulas. First, we need to find the term. The term is found using the formula for n. This formula is logarithm, future value divided by present value, divided by logarithm 1 plus I. If we put in values, it will be logarithm. Future value is 58,000 divided by 56,000 divided by logarithm 1 plus periodic rate, which is 0.04 divided by 2. N equals to 1.77205374.2. Of course, we found the same number of periods as in Excel. Now we'll use this n to find future value. Future value will be the present value, which is going to be the updated present value, 58,000. The rate is the same, so it's 4% divided by 2, because the rate is compounded semi-annually. And then we'll use the number of periods that we already found. So this n here is this n that we found. We'll just keep it in the memory of the calculator, and once we solve it, we'll find that it's going to be 60,071.43. Of course, we found the same future value as in Excel. Now, to find interest, we'll subtract our present value, which is 58,000, from 60,071.43. We'll obtain, of course, 2,071.43, which is the answer exactly as we got with Excel. In our next problem, we are asked, what nominal rate compounded monthly is necessary for an amount to triple in 20 years? How much time does it take for an amount to double at the same rate? Well, when the amount triples, it means that each dollar of that amount becomes $3. So the present value is 1 and the future value is 3. The term is 20 years and the rate is compounded monthly. First, we'll be looking for periodic rate. This periodic rate is found in Excel by the function rate. In the beginning, we'll need to find number of periods. Number of periods is, of course, the term, which is 20 years, times the number of periods per year, which is in cell B8. So B7 times B8 gives us total number of periods. Then comes payment. Because that's not annuity, we'll keep it 0. Present value is, of course, 1, which is in B5. Future value must be of the opposite sign, and that's in B6. So we'll need to make sure that we enter opposite sign for B6. When I say opposite, I mean opposite to the present value. That's very important. Otherwise, Excel will not compute correctly. Excel has to distinguish between amount incoming and amount outgoing. The end of period is what we will be selecting here. Because that's not annuity, it doesn't really matter. But if we press enter right now, we'll obtain the answer, which is in cell B10. This answer means that the rate is 0.46%, rounded to 2 decimals, compounded monthly. However, keep in mind, even though Excel shows here the rounded value, that's of course only the displaying of the number. In reality, Excel keeps as many decimals as necessary. We can increase the number of decimals to see more decimals, but we'll keep 2 decimals just to keep the result cleaner here. If we now go into cell B11, we'll need to compute nominal rate. The nominal rate is, of course, the periodic rate times the number of periods per year, which is in cell B8. If I press enter, that will be the result, which is the compounded monthly 5.51 rounded to 2 decimals. I can display that as percent rounded to 2 decimals. Once again, when I computed in B11, I used cell B10, but stay assured that Excel used all decimals of the number, not only 2 decimals, which are displayed here. For the second part of the problem, we need to identify how much time it takes for an amount to double at the same rate. So $1 should become $2. Well, to find term, we will use the function NPER. The rate comes first, and that should be periodic rate. So we'll take periodic rate from cell B10. Next comes the payment, which is 0. Next comes present value, which is in cell B13. Next comes future value, so it's in cell B14, and we'll use opposite sign for it. Then comes type, so we'll select 0 here. If I press enter, I get that it's 151.42 months. Well, we need to convert it into years, so if I can take the number of months here in cell B16 and divide by the number of periods in a year, here in B8, I'll obtain that the answer is 12.62 years approximately. So we can display the answer as 2 decimals, 12.62 years. Let's see how to solve this problem with the algebra. First, we'll use formula for I. Future value divided by present value, 1 over n minus 1. This means that the future value is 3, the present value is 1. It's 1 over 12 times 20. So the n here is 12 compounding periods per year times 20 years minus 1. If we solve this, we'll obtain I, which is 0.004588044. This is, of course, rate per month. J, which is the nominal rate, that's going to be I times 12, and that will give us 5.51% compounded monthly. We received this answer, which is exactly the same as we received in Excel. Of course, that's rounded to 2 decimals. Now, for the second part of the problem, we'll need to find n. And n is found as using logarithm, future value divided by present value, divided by logarithm 1 plus I. This gives us logarithm of 2 over 1, logarithm 1 plus I. Here, we'll just use this I here. So this I that I see here and which I will be using, that's the same I as I already found. So if I substitute this I, which I already found here, and find logarithms, the answer will be 151.42 months, rounded to 2 decimals. And again, That's the answer, exactly as the one we received in Excel. This will be finalizing the video.